Well, hello. I will start a bit about me. I've been working in big data since it was not yet a buzzword, and in particular in Hadoop and Spark for almost its beginning. The classified ad segregator Trovit was one of the first companies in Barcelona and Spain to use Hadoop for its pipelines. And in building mobile AdNetwork, our architecture and functionalities depends directly or indirectly on Hadoop and Spark. That allows me to have a good vision of how different technologies have evolved over the years and to be able to tell grandfather stories. Although Spark is only 3 years old and Hadoop less than 5, everything moves so fast that new already seems old. Here you can have my Twitter and LinkedIn accounts and email me to send any questions or wherever you want. Well, Apache Kafka. How many here have used Apache Kafka in production? Okay, good numbers. Maybe the next part will be a bit boring. Although Apache Kafka has evolved during the years, and right now, thanks to Confluence, it becomes a distributed streaming platform, in its guts, it's still a publish-subscribe message system. But what makes it great? Out-of-system can do that, but what makes Apache Kafka great and unique is its scalability, fault-tolerant capabilities, and retention system, and also that it's blazingly fast. We can consider Apache Kafka as a central point in our architecture, where applications can send messages to it, and later on, those can be processed by other applications to do something. There are a lot of different connectors already provided by the open source community for all kinds of streaming technologies and frameworks. So usually, it's easy and fast to integrate your own applications with Kafka. First of all, we should get familiar with some Kafka terminology to get started with. The message feed in our publish message system is called topic. A given topic can be used by producers to publish messages and by consumers to subscribe to them and process the stream. The broker is a server, actually a bunch of servers, that confronts a Kafka cluster and holds, receives, and sends the actual data. A topic is then split into several partitions, which will define the maximum amount of parallelism that we can achieve, but more on this later. Each partition is a timestamp sorted list of messages that producers can only write new data at the end of the partition. Each message can be located with the help of an offset within each partition. So we can refer unequivocally to them with 3 parameters: topic, partition, and offset. Although we can guarantee the order of messages along one single partition, there is no way to know, only by its offsets, the order of 2 messages of 2 different partitions. And this is important to take into consideration when we're building our applications. What really makes Kafka so fast is actually the fact that it does very little. Neither the brokers nor even the entire Kafka cluster does store the state of the consumers. Actually, Kafka provides a mechanism to do so, but it's not enforced. Many integrations do not use it. Each consumer is responsible of storing the offsets of each partition which have been already processed. In case of failure or restart, the consumer indicates from which offsets it continues reading. This can be achieved because compared to other publish-subscribe systems, Kafka has retention. It keeps the messages for a retention period and not until every consumer has processed them, basically because it doesn't know about consumer states at all. One may think that the partitioning might be a bit of a nightmare, given the problem of processing a stream of data in a fixed order or of specific semantics. However, it's the mechanism Kafka uses to split data of a single topic across different brokers. By this, it achieves more storage and even more read-write parallelism. For your application, it really provides a great boost in performance, so it's worth the hassle. But please, remember at all times that you are using a distributed system and that consumer delivers semantics are up to you, not Kafka. Kafka doesn't store the state of your consumers. It just sends you what you ask for. You have to take care of your state. A lot has changed since Apache Kafka became an incubator project. First, we got the new producer API written in Java because the prior one was written in Scala. This has reduced the dependencies in Java applications. Also, Kafka has become faster and more fully featured. However, things got really interesting with the new consumer API, basically because it merged into one the best parts of the 2 prior, separate and different consumer APIs, the high-level API and the simple or low-level API. With the latest release, 0.10, we got secure enhancements, but more exciting, the Kafka streams. Although this is not related to Spark streaming, so we won't talk about those, but you should really look at them. Well, enough for Kafka for now. How many here have used Spark streaming in production? Cool. Spark streaming enables stream processing for Apache Spark's language integrated API. That's it. letting you write streaming jobs the same way you write batch jobs. This is the main advantage. Spark streaming relies on the same API, integrations, guarantees, and semantics as Spark, batch processing. Spark streaming is built upon microbatch approach. It discretizes the input data stream into batches of data. The Spark engine continues to process the well-known basic data structure of Spark, RDDs, which are just distributed chunks of the original data. So, right now we have those discretized streams, which basically are RDDs of data from intervals of time. We can apply all transformations to them like we would do to conventionally with RDDs, because under the hood, Spark streaming engine will apply those transformations to each RDD of the stream. But how does it work and what makes it great? The so common problem of skewed data or unevenly partitioned streams can cause bottlenecks more easily on traditional systems, saturating the nodes which handle them. In Spark, we can just schedule tasks on nodes independently of the original partitioning based on available resources. Also, in case of failure, instead of reply the stream on a new spawned node, we can relaunch only the failed task on other nodes of the cluster. This, although really cool, has some side effects, as we cannot guarantee exactly one semantics for output actions. Probably you already faced this kind of problems in batch applications. In streaming applications, the problem turns out to be more notorious since your application probably will be running 24/7 non-stop. So be careful when outputting to external sources. And finally, if we mix those two together, how many have used the Kafka integration with Spark? A few less. As we said, a lot has changed over the time, both in Spark and Kafka sides, to make this integration more fault-tolerant and reliable. Here, a quick overview of the changelog, but don't worry, we will see each one in more detail. The original approach to integrate Kafka with Spark was through receivers. That was basically an Apache Kafka high-level API consumer instantiated on each Spark executor. They were receiving the messages asynchronously and stored them into the executor memory, while updating the offsets of already received messages but not processed in Zookeeper. Later on, the Spark streaming driver launched jobs to process the data already received. Although this approach works, it has very poor fault tolerance guarantees. Messages that are already received and stored in memory but not processed were lost on every restart, no the failures, etc. To solve these issues, the next version, just a few months later, 1.2, included a write-ahead log. The main idea here is to write all the information that the receiver receives on each executor into durable file system like HDFS, and not only to memory. In case of failure or loss of memory data, we can recover the state by consulting this write-ahead log. If we take a closer look, we see that not only the actual data is written into the log, we also find the metadata of the receivers that the streaming context of the driver handles. This approach, with the already existing checkpointing, leads us to a fault-tolerant solution that guarantees no data lost. As we can see, we can recover everything from our durable storage and continue from that point the stream processing. The memory data on the receivers and the metadata and the computation state on the driver. But taking into consideration that Kafka has already its own retention for recovery, this solution seems to be a bit overkill. We could just retrieve the lost information from Kafka. It makes little sense to store and process all the information again in another durable file system. Also, complexity is augmented through inflated amount of dependencies. The more you count, the more can fail. All this led to a total new approach that both simplifies the usage and improves the performance and fault tolerance. With Apache Spark 1.3 arrived a new approach of streaming integrations without the need of receivers. Also, a total new approach using Kafka Simple API instead of the high-level API and taking advantage of the core features of Kafka. It's a durable log with custom retention. It's no longer necessary to store Kafka data in buffer memory or add an additional write-ahead log because we can just ask the data directly from Kafka when we need it. So, the first step runs on the Spark streaming driver. It asks Kafka for the latest offsets on each partition of the topic. With this information, topic, partition, offset start, and offset end, the driver launches deterministic and repeatable jobs on the executors in the right order. Then each executor will process the task while retrieving the data directly from Kafka using the simple API. If a job fails due to another failure or whatever, it doesn't matter. We have not lost anything. Just reschedule the same deterministic task on another executor and retrieve the data again from Kafka. You may notice that Zookeeper dependency has gone. Since we are no longer using the high-level API, there is no need for a coordinator of the consumer group. You will still be in charge of storing and keeping those offsets offsets safe in case of driver failure or application restart. So probably you will keep storing them in Zookeeper or some other place anyway, but at least we reduce the dependencies for the basic use case. With this new Kafka integration, we do not have write-ahead logs or receivers. It allows us to have end-to-end exactly one semantics, although, as we will see later, we need something more to achieve exactly one semantics, and overall, a more fault-tolerant, efficient, and easier-to-use integration. Over the version, Spark streaming UIs received some improvements. With 1.4, adding graphics and histograms on how our application is handling the batches, we can monitor things like input rate, scheduling delay, processing time, and see, for example, if our streaming application can handle the throughput or it's lagging. And with 1.5, including metadata of the direct receivers, showing the topics, partitions, and offsets for Kafka Direct Stream. But what about the Spark 2.0 and the new Kafka integration? This is why we are here, right? So with the Spark 2.0 and Kafka 0.10, we see a split on the integration. In the Spark streaming Kafka 0.8 package, we will keep all the old integration related to broker versions 0.8 and prior, and all the new functionalities related to 0.10 will be provided by another package, which is only for Kafka 0.10 brokers. But what's really new in this Kafka integration? As we said, it uses the new consumer API provided in Kafka 0.9 instead of the simple API. And this leads to some new strategies and security enhancements. Unfortunately, there is no Python API, but probably because the API is still experimental. So we'll only have Java and Scala support right now. The new consumer API prefetches some messages into small buffers to speed up the access, but just a few. It's just a fast access buffer. This is totally not related to the all receivers approach. So we can keep the consumers cached into executors between microbatches and schedule the task on the node with the appropriate consumers. Taking this into consideration, we have 3 different location strategies. The preferred consistent just distributes partitions evenly across available executors. The preferred brokers will spawn executors on the same nodes as your Kafka brokers are located, in the case we share the same nodes for Kafka and Spark cluster. And finally, if none of these fit your needs, you can also specify a fixed mapping of partitions to specific costs. The new Kafka Consumer API also provides a very rich way to specify topics and subscriptions, but most of them will require a lot of post-instantiation setup. So consumer strategies provides an abstraction to obtain properly configured consumers for executors when they need them, even after restart and checkpointing. We are provided with 3 different ways to prescribe to Kafka topics out of the box. Subscribe to a fixed collection of topics, subscribe to a topics matching and a regular expression, or subscribe to specific partitions of a topic. If none of those fits, we can also extend the public class consumer strategy, that is a public class, and write our own consumer strategies. Since new consumer API supports SSL security, this has been added to Spark integration. But take into consideration that this only secures the communication between Kafka and a Spark. You will still need to secure communication between Spark nodes if this is needed by your use case. But God have mercy on you if you need this in your use case. Using the integration is as easy as one might expect. We just need a bunch of Kafka parameters, like the Kafka broker servers, the topics we want to subscribe with the subscribe method that we've seen before, and then build the direct stream and start applying operations to it, like we will do with any other direct stream or RDD. Having the stream, we can obtain the offset ranges and other metadata from each RDD, just casting it to an instance of hash offset ranges, and later on, using the index on each partition of the RDD, get the metadata of each partition. But wait a moment. We are talking about Kafka partition, Spark partition out of different partitions. How do they relate? Our RDDs will have as many partitions as the Kafka topic has, and we will have a 1-to-1 mapping. So we expect to see as many tasks for each stage as topic partitions has your Kafka topic. But this mapping will likely not be the same index of partition on both sides. So this line here, it's important to take into consideration if you need to map partitions of the RDD to Kafka topic partitions. Because if you use the RDD index partition to store the offsets, the mapping will surely change on each restart or even while your application is running. Also, we can use the commit API to store the offsets to Kafka itself, but I won't recommend this since it's asynchronous and cannot guarantee the same as you store it yourself synchronously. But for some use cases, as at most once or something like that, it can be more convenient than doing yourself the job. Okay, but usually the most important thing in our applications is to have guarantees that our messages are processed in the way we want. This lets us to 3 principal use cases: at most once, at least once, and exactly once. At most once means that we don't want duplicates, but we don't care if we skip some messages. For example, if you are processing some information coming from an already unreliable channel like UDP, probably some messages have already been lost anyway. If a task fails, we don't want to be rescheduled since it can produce duplicates. Also, check that a Spark speculation is false, which is by default, to avoid multiple executors running the same task. When we start the stream for the first time, we will always begin at the current largest offsets. And in this use case, we can use auto-commit offsets feature since it doesn't matter if we acknowledge some messages that don't fully process them. Taking into consideration that, this means you will almost always lose message on every restart. This is usually not desired, but if you are lucky enough to have this use case, it's probably one of the easiest ones to implement. At least once, if you don't want to lose any record, but don't care if you have duplicates, then we need failed tasks to be replayed until completed. This can be achieved by setting a virtually huge number of task max failures and always starting our stream by the beginning. Remember to disable auto-commit since it can commit not already processed messages and we don't want that. But don't be silly. Do not replay your whole retention log on every restart. Manually commit offsets when you are 100% sure that they are processed. If this is too hard, better you have a short retention log or restarts on your application will take forever. Also, if you are outputting to some external system that handles duplicates for you, like, for example, its base, you can be more flexible on offset committing. Exactly one is probably what usually you will want, but it's also the hardest one to achieve it right. So if your use case can have lower restrictions, try to go to the other semantics, please. The parameters are exactly the same that in the at least ones, but we'll need something more. We'll need some kind of idempotent writes or transactions. Usually in big data, you don't have this kind of things, but we can manage to do so, we'll see it. And only store the offsets exactly after writing the data. There is still some small chance of failure in case you don't store the offsets in the same system where you are outputting the data. Because if you write the data to HDFS and then store the offsets in Zookeeper, in this small amount of time, the application can fail and you will have lost some messages. But the chance is really small, so we can live with that. Okay, at Billy Mobile, where I work, a bit of small insights. We heavily rely on Kafka and Spark abilities. We handle like 15 billion records monthly. We have a retention log of 35 terabytes weekly, peaks of 6,000 events per second. And we have more or less all the different use cases of semantics. We will see the first one, an extract, transform, load typical operation to input events from Kafka and reach these events with some external data sources, and finally store it to Hive. We do not want duplicates. We don't want to lose any events, so this is a clear example of exactly one semantics. So Hive is not transactional. At least it's not transactional if you do not enable ACID operations. Neither has idempotent writes, but writing to HDFS is an atomic operation. You write the whole file or not at all. So basically, to achieve these kind of transactions, we establish a relation one-to-one from each partition batch in the streaming to a file in HDFS. After writing each file into HDFS, we update the current state of the batch into Zookeeper, and when we finish writing this batch, we store the new offsets to Zookeeper and continue. In case of failure or restarting, we continue from where we left it. Another use case, anomaly detector. Anomaly detector basically is to detect when something strange happens in your streaming data. For example, in our case, is to detect when an offer stops converting because it's broken, or it converts too much, for example, fraud. We do not care about losing some events because we always want to process the real-time stream. This is obviously a use case of at most once because it's useless to detect anomalies on a lagged stream. Actually, it could be very bad to take actions right now from information of the past. We always restart the stream on the latest offsets when we restart the process, the application, with a fresh state. And finally, the last use case is we need to store all our events into an entity cache like HBase to retrieve them later by its ID. We do not care about duplicates because HBase handles for us, but we don't want to lose a single event because if we lose some events, then when trying to retrieve them by ID, we won't find them. So this is a clear example of at least once. As I said, since HBase has idempotent writes, we can write events multiple times without hassle, but we don't start with the earliest offsets because writing 7 days of retention log would take like a lot of time. So every time we are 100% sure that the batch is finished reading into HBase, we update these offsets into Zookeeper and continue on. Obviously, we might have some rewriting of some events, but as I said, since we're using HBase that has idempotent writes, this is not a problem. Lessons learned for using these integrations for the last 3 years. In general, in Spark, I will discourage the use of checkpointing to save your state since it's not recoverable across code upgrades. And in this integration in particular, do not rely on commit async offsets. In general, it's more reliable to track your offset yourself in a synchronous way and store it wherever you want, in HDFS, Zookeeper, a relational database, whatever. And finally, memory is always an issue. Since the memory in our executors is statically assigned, it's difficult to adjust the throughput changes in the stream. If you have enough memory, no problem at all, but usually we don't want to waste it since it's expensive. If you are comfortable with some lag sometimes, you can adjust batch duration and max rate per partition to handle how many messages you will have on each microbatch at maximum, and don't have out-of-memory issues. Further improvements in the Spark streaming and Kafka integration, taking into consideration the memory issue, dynamic allocations may be a good solution to spawn more executors when you need them and deallocate them when you don't need. But dynamic allocation doesn't work with the Spark streaming, and there is a Riera talking about this property, Spark streaming dynamic allocation, but there is no reference at all in the documentation, and we haven't managed to make it work in our cluster. So it will be worth a try when it appears in the documentation. Also, exploring how to do better graceful shutdown of a streaming application, because right now, the most usual way to stop a streaming application is killing on the task manager, and if you have coded well all the things that we have told to not repeat the task and this kind of stuff, it's not a problem, but would be good to have a way to stop the application and finish the current batch. And finally, since the structured streaming is the new trending topic here, it would be nice to see how it relates to Kafka integration, since Kafka usually stores binary data, and we don't know a lot of the structure of the data. Thank you very much. This is all. I hope you have found it interesting. And if you have any questions, you can ask me in the last 5 minutes or on my Twitter, LinkedIn, or email. Thank you.
Great talk. Super, super informative and really interesting use case too. So yeah, looks like we already have a question. Go ahead.
Yeah, thanks for the talk. I have a question regarding the at least once guarantees. As soon as we have a write-ahead log, so why do we want to control the offsets ourselves? So it looks like the mechanism of write-ahead log guarantees us the automatic tracking of the offsets and recovery in the case of failure.
Sure. 1 second. Yes, with write-ahead log, obviously it works. But for me at least, it seems a bit of overusing resources. You are using Kafka and its hard drives to store the data, and later on you store this data again in HDFS. So you are generating duplicates and spending more resources than needed. So and also the more you have, the more can fail. And if you don't want to have HDFS at all, because maybe for some reason you don't have a Hadoop cluster, you just have a Kafka, a Spark in a standalone cluster, and you want to output the results to MySQL or whatever, I think it's not worth to have HDFS in this situation just to ensure that everything works fine. And more taking into consideration that the new approach just works better and fine.
Okay, yeah, makes sense. Thanks a lot.
Thank you.
Hi, I was wondering if you could go into a little more detail on how the 0.10 consumer offers you that exactly once guarantee in a way that the 0.8 consumer did not. Because it seemed like, so in the 0.8 consumer, you said that as long as your sync is idempotent, you would achieve effectively exactly once guaranteed, but I didn't see how the 0.10 consumer would give you that if your sync is not idempotent.
Okay. Achieving exactly one semantics in Spark is difficult, especially for output operations. And your intermediate operations can be repeated, obviously, but usually you will only care for the output part. So in the previous integrations, it relies in the fact that the executors has stored the messages in a buffer, so it can fail more because losing the memory data. In this case, since a task failed, you just reschedule the job again. Then the executor will start from the beginning, retrieving the information from Kafka. And as I have said, exactly once is the most difficult because you need an external thing not provided by Spark to achieve it. You need some kind of transaction that you start a transaction, start writing the data, and if something fails, the transaction is aborted and nothing is written. Or you need some kind of idempotent writes. I know this is not an ideal case scenario, but with Spark, nothing more can be achieved. You need to rely on some external system that provides you this transactional feature.
Yeah, so basically you can either repeat, if the sync allows you to sort of repeat a write, then it's no problem, right? But just sort of like what you're describing and what we saw in the keynote, a really important part of it ends up being sort of transactions so that you can either know that something happened or something did not. And I think that Spark streaming has a fair amount of challenges around that sort of low-level stuff. And just sort of like you're showing in your presentation, you're like tracking offsets yourself and then launching tasks and stuff like that. And it's a lot of just sort of incidental complexity, right? And
it's a lot of low-level work that ideally would be done by the Spark streaming framework.
Yeah, exactly. And then you want to get rid of that, and so you don't want to have HDFS, and so then you track offsets yourself, so you don't have to have that distributed store, et cetera. I think there's just sort of interesting trade-offs in terms of managing complexity, and yeah, I think that Spark continues to improve on that, but I think Spark streaming has a little bit more room to grow, I'll put it that way. Cool. So with that, let's give a hand and we'll prep for the next talk.
Thank you.